Lesson 38, demo. In this class, we introduced the definite integral as well as the integral symbol. We also discovered that the more rectangles, the better. In the last class, we estimated area under a curve by drawing right rectangles as in this picture. Notice that in this picture, in each interval, for example, this one right here, of the two endpoints, the one that we chose to determine the height of the rectangle was the right-hand one. That's why these are called right rectangles. And that dictates the height of the rectangle, and then we complete the rest of the rectangle. We could just as well have let the left endpoint of each interval determine the height of each rectangle. Likewise, we could have used the midpoint of each interval. Really, any point in between each interval would be just fine. In the last class, we saw this messy formula. Let's talk through it again to make sure it seems reasonable. Okay, so here's our right-hand sum. Let's take a look at, I will draw this rectangle here. Between those two endpoints, we're going to pick the right-hand one to dictate the sum. That's up here. So if I want the area of that rectangle, then I know the area is base times height. And we let delta t represent the base of each of these rectangles. So the base is delta t times, and then the height is just the y value at this right-hand endpoint right here. And you'll recall that we let t sub 1 be the coordinate of that right-hand endpoint. T sub 2 was there, and t sub 3 was here. And the very beginning guy we call t sub 0. And so the area of that green rectangle, base times height, delta t times f of t1. That's the height of that rectangle. And then the area of the orange rectangle, again, is base times height. Bases are all called delta t, and the height of the orange rectangle is the function value at its right-hand endpoint, which is called t2. And so if we continue on in this pattern, the area of all the rectangles added up is delta t times f of t1, we saw that, plus delta t times f of t2, we saw that one, all the way down to delta t times f of t sub n. Okay, and then last class, that particular function, the curve up here, was supposed to represent the velocity of somebody running a race or something. And we discovered that the area under the curve, between the curve and the horizontal axis, is actually the exact distance traveled by that person. And we approximate that curvy area with rectangles, because those are shapes that have areas that are easy to calculate. So really, we wrote area here, but we were approximating the distance traveled. The sum is called the Riemann sum after George Bernard Riemann. We can use sigma notation, like in the regression project, to abbreviate the long formula above. So here it goes. Distance is approximately equal to, okay, big sigma, capital Greek S. We're trying to capture the pattern of each of the terms separated by all these plus signs, and every single one of those terms looks like delta t times f of t something. Delta t times f of t something, and the something is that blank space down at the bottom, and all we're going to do is give it a name. We're going to put a letter down here to represent the generic nature that all we're doing is putting a 1 or 2 or 3 or an n. So let's call it an I. So if we call it I, what we're supposed to do at the bottom of the sigma is write down the starting value of I, and the starting value of I is actually 1. That's the very smallest I that's in our expression. So this one goes from I equals 1 up to, and then the ending I, the very last value, is n. And so that is the compact sigma notation way of writing all of this. So instead of writing all of that, you can just write the shorter sigma notation version. What can we do to get better and better approximations for the exact area under the curve? Well, we can use more and more rectangles. Let's take a look at the left-hand picture. First of all, for example, for this rectangle right here, which point is the one that is used to determine the height of that rectangle? It's actually not the left-hand point, because the left-hand point would give that rectangle. It's also not the right-hand point, because the right-hand point would go all the way up to here. In this case, it's maybe the midpoint. The midpoint is the one that we're looking at here. If you look at the midpoint of this interval, and you go up to the height, and then you draw left and right to complete it to a rectangle, that is a midpoint rectangle. So these 3 pictures all have midpoint rectangles, just for some variety. And you can see that if we're trying to find the exact area under the curve, that exact area right in there, the 5 rectangles do an okay job of approximating it. You can see that we miss some area right here. The rectangles don't capture that, but we also get some extra stuff that's above the curve that we didn't want. So it's not a terrible approximation. But surely when we use, I don't know if that's 10 rectangles there, it's better than the 5 in the previous picture, because the stuff that we miss is smaller and the stuff that we accidentally get is smaller. And then in the 37 rectangles, you can count them. Here, you can't even tell. I mean, I know for sure we're getting some extra stuff and it's tiny, and we're missing some extra stuff and it's also tiny. As n increases, the area of the rectangles approaches the exact area under the curve. So putting all of this together, here's the full-fledged, hardcore, no messing around definition for the area under a curve. If the function f is continuous on the interval a, b, and if f of t is bigger than or equal to 0 for all t in a, b, then the area under the curve y equals f of t over the interval a comma b is defined by a equals limit as n goes to infinity, summation I equals 1 to n delta t times f of t sub I. Woohoo! Okay, we saw right here, this summation, it is copied symbol for symbol on the next page. So that is this part of it, which is most of it. And the only thing that is new is this limit. And remember, n is the thing that represents the number of rectangles. And so how many rectangles do we want? Well, if we want the actual exact curvy area, then we want infinitely many rectangles. And so we take the limit as n goes to infinity, and that limit is equal to the actual curvy area. This formula isn't something you need to memorize, but calculating area under a curve is something we'll do many times, so we will use some new notation to avoid having to write the formula above. This new notation is super important in any future calculus classes you take, for example, Calculus 2. All right, so brand new symbol for us. Funny curvy shape here with an A and the B on the top and the bottom. F of t dt, that part doesn't look intimidating. We're gonna let all that entire symbol right there denote the area under the curve y equals f of t over the interval a comma b. A comma b, remember, is just the input values. So, you know, from like here is a, and then over here is b. Okay, so said another way, if you see all of these crazy symbols, we are really just talking about that hardcore area, exact area definition from above. The symbol, this funny new symbol here, I've omitted the function in there, but that entire symbol is called a definite integral. The numbers on the integral sign, so the integral sign, I guess, is this funny, almost S-shaped thing there. That's the integral sign. The numbers on the integral sign are called the limits of integration, not to be confused with all of the limits we've been calculating this year. The function y equals f of t is called the integrand. So brand new vocabulary, all associated with area under a curve. Typically, we use x as our independent variable, so our integrals will often be of the form, and I'll read this out loud now, integral from a to b of f of x dx. Again, integral from a to b of f of x dx. For example, what does the integral from 0 to 3 of x squared dx mean? Let's draw a sketch and do some shading and then estimate the answer by drawing a triangle. Okay, here's what we're going to do. We are going to graph the function f of x equals x squared. Remember, that is called the integrand. So that's our friend, the parabola hits there at the origin. And we are interested, this whole symbol here tells me it's talking about the area, and it's the area between x equals 0 and x equals 3. So we label those points. So there's x equals 3, and here's x equals 0. And we're just going to go up to the curve, land someplace up here. And so that symbol right there, I'll highlight it here. This symbol in yellow really means the area of that space in there. I guess my highlighter is too thick to really draw it in. So it's the area of this space right here is exactly what is meant by this symbol. Okay, so can we estimate that answer? Because I sure don't have a formula for the area underneath a parabola. But that parabola, that shape right there, the red shape, is almost triangular, right? So how about we just pretend, we'll be friendly with each other and pretend that it is a triangle. So I'm going to connect the dots here, the 0 and the 3. And I'm going to calculate the area of this big triangle here, which includes the red and also includes a little bit extra stuff. So we're going to overestimate the exact area. So let's practice writing our brand new symbol. Integral from 0 to 3 of x squared dx is approximately equal to the area of that triangle, which is a 1/2 base times height. The base of that triangle is 3. The height of that triangle we haven't found yet, but it's whatever the function is at 3. And this is the square function, so this is 9 over here. And so we get 27 over 2, 14.5 is our approximation for that area. Of course, the true area is going to be a little bit less because our triangle includes that extra white space above the red curve area.